About for class, we talked about 205B, the writing assignment we had. And I didn't record it during class, so I'm recording it here after class just to make sure you have something to go back and look at. But with that, that assignment told us, it actually asked us a question. That's what I had to do. How could you use Descartes' rule and the fundamental theorem of algebra to predict the number of complex roots to a polynomial? All right. So what you had to do is you had to, first of all, give a summary of Descartes' rule and the fundamental rule of algebra. And, just in your own words, I'm not looking for a textbook definition. I'm looking for you understanding what that means. And then you had to give two examples. So you're making up two polynomials. And from those two polynomials, you're using the fundamental rule of algebra and using Descartes' rule to predict the number of complex roots, because that's what this is about. How can you use those to predict the number of complex roots? Remember, complex roots are imaginary roots. 6 plus 2i, that's imaginary. And if you have 6 plus 2i, that means you have 6 minus 2i. Remember, complex roots come in pairs if it's a root of a polynomial. So you're supposed to use complete sentences, appropriate grammar and spelling, all that good stuff. And then use what source did you get your information from? You look up Descartes' rule. Did you use a website or what did you use? And you need to give the reference at the bottom of your writing, because this is formal writing. And so we need to reference those things. So with that, I gave an example here in class. I want to look at that and just go over that real quick. So here is the equation that I used in class. 4x to the fifth minus 3x to the fourth minus 2x to the third plus x squared plus 7x minus 1. And with that, we check to see how many sign changes. We know the fundamental rule of algebra said that there will be 5 roots, guaranteed, because it's a fifth power, right? Earlier, we said there would be up to 5 roots before we got the pre-cal, because we never considered complex roots imaginary roots. But now that we know imaginary roots exist, there are 5 roots according to the fundamental rule of algebra. Descartes says if we count the number of sign changes, like it went from a positive to a negative, negative to a positive, positive to a negative, 3 sign changes, I have them highlighted. That will tell us the number of positive roots, right? Positive roots that this equation might have. There might be 3, or there might be 1. All right, there might be 3, there might be 1, because if they're not all positive roots and some of them are imaginary, they're going to come in pairs, right? Complex roots come in pairs. So if there's not 3, there's only going to be 1. There's not going to be 5, because Descartes' rule tells us there's not 5, but there might be 3. And then using Descartes' rule, we can substitute negative x in. I've underlined all these negative x's, right? And when we simplify that, negative x to the fifth power ends up a negative, so it's negative 4x to the fifth. This one ends up a positive to the fourth power, so it stays negative 3 times x to the fourth. And we simplify that all the way across. And then from that, we count the sign changes again. There's 1 sign change there, and there's 1 sign change there. Negative, negative, positive, positive, negative, negative. So that tells us the number of negative roots that are possible. Again, not guaranteed, but possible. There could be 2, or there could be 0. So we use Descartes' rule to figure out how many possible roots. And from that, we're going to combine these 2 rules. The fundamental rule of algebra tells us there has to be this many. Descartes tells us there could be any of these combinations to predict the number of complex roots for our polynomial. If there are 3 positive and 2 negative, that means there's no complex roots. There's no imaginary roots at all, because there's all 5 of what's possible. If it's 3 positive and 0 negative, that leaves room for 2 imaginary roots. Or if there's 1 positive root and 2 negative, again, that's 3 real roots and leaves room for 2 complex roots. And then in this scenario, if there's only 1 positive root and 0 negative roots, there's only 1 real root. That's going to mean there's 4 complex roots. Now I have these highlighted because during our lesson in class, we went ahead and graphed it just for fun. We didn't have to graph it. The assignment does not ask for a graph. That was just for us to confirm what we were saying here. And we graphed it, it looked like this. All right, we went to Desmos, we threw this equation in there, and there was only one real zero, 1 real root, and it was like at 0 point, I think it was 114. And it was a positive root because there's only 1 of them. Well, if there's 1 of them, it should have been positive because we didn't predict there could be 1 negative. All right, the negative one, 2 or 0. There was just 1 root. It was a positive root, so we know that was true. There was 0 negative roots because we didn't cross anywhere over here. So there was only 1 real root, which means there's 4 imaginary. Now, this doesn't ask us to find those 4 imaginary. It doesn't even ask us to confirm that there's 4. It just wanted us to predict how many there could be. And there could have been 0. It could have been 2. That turns out it was 4, and we predicted that. So just remember, subtracting 2. You know, if this would have been an extra 6, that means there could have been 6 roots. If there was a sign change every time, and we counted 6 sign changes, or 6, that means it could have been 6, but it could have been 4, 2, or 0, because if any of these roots are imaginary, they're going to come in pairs, right? Going to come in pairs. You're going to have 2 complex roots each time. So that means it'd be down to 4 or down to 2 or down to 0. So don't forget, when you're predicting this, you also have those subtract 2 options that predicts perhaps there's 2 less than we think there are. So, but this is what the assignment was all about. We had to do that. You had to first, give a summary of what those rules mean, just in your own words. Then 2 examples. This was 1 example that I did. I did 1 example. I used the fundamental rule of algebra to figure out how many total roots there were. Then I used Descartes' rule to figure out how many possible positive, how many possible negative they were. And then, using both those rules in combination, I predicted how many complex roots there might be, which was the 0, the 2, or the 4. All right, so that's what that assignment is all about. 205.b. If you did that assignment and did not understand that and missed that and want to redo that, that's fine. Just let me know. I'll click on Buzz, let you retake it. You can rewrite that, or you can just email it to me and say, okay, I understand this better. Let me write this paper and explain it with 2 examples. And then I'll know that you have understand that. That's an evidence of learning grade, and I will see you have learned more. That's good evidence that you have learned more if you want to rewrite that, if you didn't do well the first time. But if you have questions on that, get with me. It's kind of cool how we can take these things and really learn a lot more about these polynomials than we ever knew before by applying these rules and just seeing what it tells us. So that was class this week. We have a test. We have the practice test to help us make sure we're ready for the test. Practice test. Then we have the test, and we have to do the first lesson in Unit 3. We're having to kind of pack some stuff in here to get things done. We got a lot to cover this year. So we're doing lesson 1 also this week. But that's all that's due this week. Just 1 lesson and the test. I say that's all, right? It's a test. That's right. You guys are getting this down. You're understanding. You're doing well. If you have any questions, email me or get with me or come to a meet, and we'll work through some examples and help you understand. So have a great week.
Let's get out of here. Word to your multiples. Math, baby. We're learning math, baby.